If you're a software developer or just getting started in coding, you've probably heard the term unit testing tossed around quite a bit. But what exactly does it mean? And why should you care about it? Well, in this video, we're diving deep into the world of unit testing, why it's so important, how to write testable code, and the best practices you can follow to make sure your software is rock solid. Let's get started. Unit tests are only one piece of the puzzle when it comes to testing your software. There are other types of tests like functional tests and integration tests, but unit tests are the smallest, fastest, and most isolated form of testing, which makes them incredibly useful during development. Scenario or large-scale tests focus on testing the entire application from the perspective of a user. These tests simulate a full user interaction and typically involve real user data. They can take a long time to execute and often rely on real infrastructure, which can make them flaky and slow. They are useful for confirming that all components work together as expected, but they're not the most efficient way to find bugs during the development process. For example, in an e-commerce app, a scenario test might simulate a user browsing products, adding them to the cart, and completing a checkout process. It tests the system as a whole. Functional tests, also called medium tests, strike a balance between unit tests and scenario tests. These tests focus on testing specific subsystems or modules of the application, but use simulators or mock dependencies instead of real ones. You can think of the relationship between these three types of tests as a hierarchy of scope. Scenario tests focus on the entire application and simulate real user interactions. Functional tests narrow the scope to specific subsystems or modules and use mock dependencies. Unit tests break it down further, targeting individual classes or functions, ensuring they work in isolation. In essence, you're testing from the broadest level to the most granular level. So, first things first, what is unit testing? At its core, unit testing is a software testing technique where individual units, or small parts of a program, are tested in isolation to make sure they're functioning as expected. These units can be individual methods, classes, or functions. The goal here is to validate that the smallest pieces of the application work perfectly on their own, which ultimately ensures the entire system works as expected when everything's pieced together. Unit tests are typically very fast, can be automated, and run frequently to catch issues early. Think of them like safety nets. They help us catch bugs in the early stages of development before they can cause bigger problems later on. Now that we understand what unit testing is, let's take a look at why it's such a crucial part of the development process. From catching bugs early to ensuring better code quality, unit tests offer several key advantages that make them an essential tool for developers. Now that we know what unit testing is, let's dive into why it's so valuable. Unit testing brings a multitude of benefits to the development process, ensuring that your code is reliable, maintainable, and efficient. Let's take a look at some of the key benefits. First and foremost, unit testing helps catch bugs early. And as we all know, finding bugs early in the development cycle is significantly cheaper than finding them later. Think of unit tests as safety nets. If there's an issue, you'll know right away before it becomes a major problem down the road. Unit tests also give developers confidence when refactoring code. If you need to make changes to your code, unit tests act as a safety net, ensuring that the modifications don't break existing functionality. This makes refactoring easier, safer, and less risky. Next, unit tests can serve as documentation for your code. By writing tests, you're essentially documenting how the individual units of your system are supposed to behave. If another developer looks at your unit tests, They can quickly understand how a unit is expected to work and what edge cases need to be handled. Another huge benefit of unit testing is that it enables faster iteration and more frequent releases. Because unit tests test individual components in isolation, developers can identify and address issues in those specific components quickly. This leads to faster development cycles and ultimately allows you to release more frequently with higher confidence that the changes won't break anything. Unit tests help ensure that your software meets its design specifications and behaves as expected. By testing the smallest testable units first and then combining those tests, you can create comprehensive tests for more complex applications. This ensures that each part of the application is performing its role correctly. As mentioned earlier, finding bugs early is a major cost saver. The sooner you can catch issues, the cheaper it is to fix them. Unit tests help you identify bugs in the code early, which saves both time and money and reduces the risk of expensive bugs in production. Now, let's talk about the things that can make your code nearly impossible to unit test. Understanding these pitfalls is key to writing clean, testable code. Let's break them down. First up, mixing business logic with object creation. Imagine you have a class that handles user authentication, and inside that class, you're creating a new database connection or a new API client. Now, if you want to test just the authentication logic, you're stuck. You can't easily isolate the logic from the database or API. This makes your tests slow, fragile, and dependent on external systems. Next, global state and singletons. These are often the hidden culprits behind flaky tests. Global state introduces hidden dependencies between tests. If one test modifies the global state, another test might fail unpredictably. Tests should be independent of one another, and global state breaks that independence. Similarly, singletons are essentially global state disguised as a class, making them just as problematic. Another common issue is overcomplicated inheritance hierarchies. Deep inheritance chains are hard to test because changes in a parent class can ripple through multiple child classes. It's like trying to pull one thread and unraveling the whole sweater. Static methods are another roadblock. Since they belong to the class itself, rather than an instance, they can't be easily overridden or mocked. If your code relies on static methods, you're forced to test them as is, which might mean relying on external systems or complex logic. Finally, having too many conditionals or mixing responsibilities in a single method or class. When a method tries to do too much, like handling file input, processing data, and sending a network request, it becomes a nightmare to test. You have to cover all possible paths, inputs, and interactions, making the test suite large, slow, and complex. So, to recap, here's what makes code hard to test. Mixing object creation with logic, relying on global state, deep inheritance chains, static methods, and overloaded methods with too many responsibilities. Avoiding these pitfalls will make your code cleaner, more modular, and, most importantly, much easier to test. Now that we understand the importance of unit tests, let's shift gears and talk about something even more fundamental: writing testable code. Because here's the truth: if your code isn't written with testing in mind, writing effective tests becomes significantly harder, if not impossible. First, follow good object-oriented design principles. This means things like keeping your classes focused on a single responsibility, adhering to solid principles, and avoiding deep inheritance hierarchies. Well, classes that are designed with a clear single responsibility are easier to understand and, more importantly, easier to test. Why? Because they have fewer dependencies and less complexity. This reduces the chances of things going wrong and makes it easier to pinpoint issues during testing. For example, instead of having a single class that handles user authentication, database queries and logging, split those responsibilities into separate classes. This modular approach simplifies both the code and the tests. Second, use dependency injection to inject dependencies into your classes instead of creating them internally. If your class needs a database connection, hard coding it inside the class might seem convenient, but it tightly couples your class to that specific implementation. This makes it difficult to test in isolation because you'll always need a real database connection. Instead, pass dependencies like the database connection through the constructor or a method. This allows you to easily swap out the real database connection for a mock or stub during testing. Next up is test-driven development, or TDD. This is a development approach where you write tests before you write the actual code. Okay, so now you're ready to start writing tests. But where do you even begin? This is where test-driven development, or TDD, comes in. TDD isn't just about testing, it's an iterative process that shifts how you approach coding. Here's how it works. First, you write a test for a feature or function you need to implement. This test starts off as a failing test because, well, the code doesn't exist yet. Next, you write just enough code to make that test pass. You're not aiming for perfection here, just functionality. Finally, once the test passes, you refactor your code. This step is crucial. You clean up your code, optimize it, and ensure it's following best practices, all while making sure the test still passes. The great thing about TDD is that it forces you to think about the requirements of your code before you even start writing it. And that's powerful. Instead of diving straight into writing code and figuring things out as you go, you start with a clear blueprint of what the code needs to do. You avoid over-engineering by focusing only on what's necessary to meet the requirements. You catch potential design flaws early because you're constantly testing as you go. And perhaps most importantly, you end up with better designed, more maintainable code in the long run. So, if you're ever unsure of where to start when writing tests, remember, TDD is your guide, helping you write code that's reliable, maintainable, and built to last. So, what makes a good unit test? To help you remember the key characteristics of a good unit test, think of the acronym ATRIP: automatic, thorough, repeatable, independent, and professional. Let's break it down. First, automatic. A good unit test should require zero manual effort to run or verify the results. This means the test should be part of your automated testing suite, triggered whenever code changes are made. The test should automatically invoke the necessary code and automatically check the result without human intervention. Next is thorough. Your tests should cover a wide range of scenarios, including edge cases and error conditions. Code coverage is a good metric to track, but it's not just about hitting every line of code. You need to think about different types of inputs, valid, invalid, boundary cases, and ensure your tests handle them all. For example, if you're testing a function that calculates discounts, make sure you test normal purchases, $0 purchases, and negative input values to ensure the function handles all cases correctly. The third characteristic is repeatable. A good unit test should produce the same result every time it's run, no matter how many times or where it's executed. This means your test shouldn't rely on external factors like the system clock, network connectivity, or random values. If your test passes one day and fails the next for no apparent reason, it's not a reliable test. Next is independent. Each unit test should be self-contained and not rely on other tests to run or pass. If one test relies on the outcome or setup of another test, you've created a fragile testing structure. A failure in one test can cascade, causing others to fail even if they are unrelated. And finally, professional. Your test code should follow the same standards of design and quality as your production code. So, remember a trip when writing your unit test. Now, while unit tests are essential, they are not a silver bullet for ensuring software quality. It's important to understand their limitations. First, unit tests have a limited scope. They only verify the functionality of individual components in isolation. This means unit tests can't guarantee that the system as a whole will function correctly. They don't test how different components interact with each other or whether the entire application works as expected. Second, relying too heavily on unit tests can lead to false confidence in your software's quality. Passing unit tests might give the impression that the software is ready for deployment, but without integration or system tests, critical bugs can still slip through. These could be related to data flow, network issues, or even race conditions that only surface when components interact in a live environment. Let's talk about a concept that often confuses developers: test doubles. These are tools we use to replace parts of a system during testing. The two most common types are mocks and stubs. While people often use these terms interchangeably, they actually serve very different purposes. First up, stubs. Stubs are all about controlling behavior. They provide predefined responses to method calls during a test. For example, let's say you're testing a function that calculates a user's order total. Instead of making an actual database call to fetch product prices, you can use a stub to return fixed prices for those products. The stub doesn't care if the function interacted with it correctly or how many times it was called. It's just there to provide consistent data. Now, mocks serve a different purpose. While stubs focus on what data is returned, mocks are all about how the code interacts with the mock object. Mocks are used to define and verify interactions. They expect certain methods to be called, possibly in a specific order, with specific parameters. If these expectations aren't met, the test fails. Martin Fowler highlights that this distinction reflects two different testing philosophies: state-based testing versus interaction-based testing. Stubs focus on testing the state of the system after a method is called. You're verifying the output or changes in state. Mocks, on the other hand, test the interactions, ensuring that the right methods were called with the right data at the right time. If your goal is to test the output or final state of a unit, use a stub. But if you need to verify that specific interactions occur between components, a mock is the better choice. What makes software components testable? Let's break it down into key factors. Controllability. Can you easily control the inputs, preconditions, and environment of the component under test? More control means better test scenarios and coverage. Observability. Can you observe the internal state and outputs? If you can't see what's happening inside, it's hard to verify correctness. Isolatability. Can the component be tested independently? Isolating it reduces noise and makes defect identification easier. Separation of concerns. Does the component have a single, well-defined responsibility? Components that follow the single responsibility principle are easier to test. Understandability. Is the component well documented or self-explanatory? Clear code is easier to test and understand. Automatability. Can the component's tests be automated? Automation improves efficiency and integrates seamlessly with CI/CD pipelines. Heterogeneity. Does the system require diverse technologies? More technologies often mean more testing strategies and tools are needed. By considering these factors, you can design more testable, reliable, and maintainable software components. All right, let's quickly recap what we've covered so far. Unit testing is all about validating individual pieces of your application in isolation, ensuring they work as expected before they're integrated with the rest of the system. We've explored the benefits: catching bugs early, supporting refactoring, acting as a form of documentation, and even enabling faster, more frequent releases. But writing good unit tests starts with writing testable code. This means following solid object-oriented design principles, using techniques like dependency injection, and avoiding tightly coupled or overly complex code that's difficult to isolate and test. We also introduced test-driven development, or TDD, an approach where you write your tests before the actual code. This not only helps clarify requirements, but also leads to better designed, more maintainable software. Finally, we touched on the limitations of unit tests. While they're essential for ensuring code quality at a granular level, they don't cover system-wide interactions, external dependencies, or complex user interfaces. That's why it's important to complement them with integration and system tests for a more comprehensive testing strategy. Unit testing is a powerful tool, but it works best as part of a balanced testing approach that covers all aspects of your application. Now that we've discussed unit testing and how to write testable code, let's talk about one of the most popular tools for unit testing in the Java ecosystem: Junit. So, what is Junit? At its core, Junit is a powerful unit testing framework specifically designed for Java. It enables automated testing of individual components, making it easier to verify that each part of your code functions correctly. Instead of manually testing your code every time you make a change, Unit allows you to automate those tests, saving you time and reducing human error. Junit is also a must-have tool for test-driven development, or TDD. Since TDD encourages you to write tests before writing your actual code, Junit provides the structure and functionality to seamlessly integrate testing into your development workflow. In short, Junit helps you catch bugs early, automate your tests, and build reliable, maintainable Java applications, all while supporting best practices like TDD. Alright, now that we've covered the basics of unit testing and JUnit, let's dive into how you can start writing basic tests using JUnit 5. First things first, let's make sure JUnit 5 is set up in your Java project. If you're using Maven, you'll need to add the JUnit 5 dependencies to your pom.xml file. Here's the basic configuration. Once the dependencies are set up, you're ready to start writing your tests. Let's write a simple unit test. Imagine you have a calculator class with an add method. We want to test that the add method works as expected. Now, let's create a test class called calculator_test. In JUnit 5, we use annotations like @test to mark a method as a test case. Now that we have our test, let's run it. If you're using an IDE like IntelliJ or Eclipse, you can simply right-click on the test class or method and choose to run it. Once the test runs, you should see that it passes, which means the add method in our calculator class is working as expected. Let's break down what's happening here. @test. This annotation tells JUnit that the method below it is a test case. Assert equals expected actual. This is an assertion method. It checks whether the actual result from the code matches the expected result. If they match, the test passes. Otherwise, it fails. That's the basics of writing tests with JUnit 5. Let's take a look at some more assertion methods. Assertions are the heart of unit testing, as they allow you to verify that the actual output from your code matches your expectations. JUnit 5 has a variety of assertions that cater to different testing needs. So let's explore some of the most commonly used ones. Assert equals expected actual. We've already seen this one in action. The assert equals method checks if two values are equal. If they're not, the test will fail. It's the most common assertion method. Assert not equals expected actual. If you want to ensure that two values are not equal, you can use assert not equals. Assert true condition. What if you just want to check if a condition is true? Use assert true to verify that a condition evaluates to true. Assert false condition. Similarly, if you need to test whether a condition is false, you can use assert false. Assert null object. What if you want to ensure that an object is null? Use assert null. Assert not null object. On the flip side, you can use assert not null to ensure an object isn't null. Assert array equals expected actual. If you're working with arrays, JUnit has a special method to compare them. Assert array equals. It verifies that two arrays are equal. It checks if they have the same length and all corresponding elements are equal. Assert throws expected type executable. Sometimes you want to verify that an exception is thrown when a certain action is performed. JUnit 5 provides assert throws for this. These are some of the most common assertion methods in JUnit 5 that you'll use frequently when writing unit tests. Whether you're checking for equality, verifying conditions, or ensuring exceptions are thrown, these assertions will help you ensure your code behaves as expected. Now that we've covered the basics of unit testing with JUnit 5, let's take a look at a powerful tool that can make your tests even more effective: Mockito. Mockito is a popular mocking framework for Java, widely used in unit testing. It allows you to create mock objects, essentially fake implementations of real objects that are used in your tests. In unit testing, we often need to isolate the unit of work, which means we might want to replace some of the dependencies of the class we're testing with simplified versions. This is where Mockito comes in. Mockito helps you create mock objects for classes or interfaces that your unit of work depends on. Instead of interacting with real dependencies, such as databases or external services, Mockito lets you simulate their behavior. It's important to remember that Mockito is a mocking framework, while JUnit is a testing framework. They work hand in hand. JUnit provides the test structure and assertions, and Mockito helps you isolate your unit by mocking external dependencies. By combining JUnit and Mockito, you can write comprehensive isolated unit tests that are faster, easier to maintain, and more reliable. We've covered a lot of ground today, so let's take a moment to recap everything we've learned. Unit testing is a fundamental practice in modern software development, allowing us to verify that individual components of our application work as expected in isolation. By writing unit tests, we can catch bugs early, improve code quality, and ensure that our application remains robust as it evolves. Unit testing brings a lot of benefits. It helps you catch bugs early, facilitates refactoring, ensures your code meets design expectations, and even serves as a form of documentation. Perhaps most importantly, it makes your development process more predictable and reliable, enabling more frequent releases and smoother integration. But as we discussed, unit tests are not a silver bullet. They are limited in scope and can't test the entire system. That's why combining unit tests with integration and system tests is key to ensuring overall application quality. As we dive deeper into writing unit tests, we can't ignore the importance of writing testable code. If your code isn't designed with testing in mind, writing effective unit tests can be a challenge. Next up, we explored test-driven development, or TDD. With TDD, you write tests before you even write the code. This encourages you to think about the requirements up front and ensures that the code you write will fulfill those requirements. TDD helps you avoid overcomplicating things and ensures that each piece of your code serves a specific purpose.